Okay, let's unpack this one. We've got a really interesting deep dive today, and it's based right on the sources you shared.
Yeah, it's a great example, actually.
Right. How, like, abstract math isn't just for textbooks. It helps us understand, well, real world stuff.
Exactly. And today we're looking at something pretty common, drying herbs and vegetables grown on farms.
And how math fits in.
Specifically, how integration, from differentiation and integration studies helps figure out nutrient loss during that drying.
It does seem a bit weird at first, doesn't it?
Yeah.
Calculus and drying basil.
Yeah. But think about it. Drying isn't just water removal.
Right.
It's dynamic. There are chemical changes happening. Nutrients break down. They get lost over time.
Ah, right. And your sources pointed out that the rate this happens isn't steady.
Exactly. That's the tricky part. It might be faster early on, maybe slower later. Depends on the nutrient, the heat, airflow, that kind of thing.
So,
Ah.
okay, if the speed of loss keeps changing,
Yeah.
how do you know the total loss at the end? You can't just like pick one speed and multiply by the time, can you?
No, you definitely can't. And well, that's precisely where integration comes in. It's the tool for summing up those continuous changes.
Okay.
So if you can describe that changing rate of loss with a mathematical function, integration over the drying time gives you the total amount lost.
Ah, I get it. It's like finding total distance when your speed keeps changing. You integrate the speed.
That's a perfect analogy.
Here, the speed is the rate of nutrient loss, and the distance is the total nutrient gone.
Precisely. The sources mention researchers doing experiments, right? Measuring nutrients at different times during drying. And from that data, they can often create a model, a function, for the rate of loss over time. Might be exponential decay, something else.
Depends on the situation.
Exactly. And once they have that rate function, they use the definite integral over the time period.
And that gives them the total loss number.
Yes, a concrete number.
But like, okay, we lost 25 milligrams of vitamin C in these peppers after 8 hours, something like that.
Exactly like that. Or maybe we kept 70% of the essential oils in these herbs. It gives them a real quantity.
And knowing that total must be super useful for farmers, food scientists.
Oh, absolutely. It lets them tweak things, optimize the drying temperature, the time.
You keep more nutrients in.
Yeah, exactly.
Yep.
While still getting it dry enough to preserve. They can compare methods, too. Method A versus method B, which one loses fewer nutrients. Integration helps quantify that difference.
Wow. So it directly impacts, the quality you get in the end.
It really does.
It just shows how these math tools, like finding the area under a curve, which is what integration fundamentally does, it translates directly. It's not just abstract anymore. It's about measuring real changes to make, well, better food.
So just to kind of wrap up the main point, integration isn't just theory.
Right.
It's about adding up the effects of something that's constantly changing, like nutrient loss during drying. You model the rate, you integrate it, and boom, the total loss.
Yeah, it connects the math class concepts, right, to practical stuff, like preserving food better. It's pretty cool.
It is.
And it makes you think, where else is integration hiding in plain sight, helping us understand how things change around us, from drying veggies to who knows what else you might find, something to think about.